Hello student. In previous video lecture we have seen that the probability mass function of geometric distribution and mean and variance of geometric distribution. Now in this video lecture I am going to explain the mean and variance of another form of geometric random variable y equal to x plus 1, then moment generating function of geometric distribution and cumulant generating function of geometric distribution. Now first we see the mean and variance of the geometric random variable y equal to x plus 1. Okay, we know that probability mass function of geometric random variable x, if x follows geometric distribution with parameter p, then its probability mass function is x equal to small x, which is equal to p into q raised to x. X takes values 0, 1, 2, 3 dash 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 0 otherwise. Okay, here 0 less than p less than 1 and p plus q is equal to 1. Then the expected value of this random variable x is equal to, that is mean of the geometric distribution is equal to q upon p, and variance of random variable x is equal to q upon p square. This is the mean and variance of the random variable x that follows geometric distribution with parameter p. Now suppose this y is equal to the number of trials required to get the first success. Therefore this y is equal to x plus 1. Y is equal to x plus 1 is the number of trials required to get the first success. Therefore the probability mass function of random variable y will be probability of y equal to small y, which is equal to p into q raised to y minus 1. Here y takes values 0, 1, here y takes values 1, 2, 3 dash 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 up to infinity. That is, support of this random variable is 1, 2, 3, 4 up to infinity and 0 otherwise. This is the probability mass function of random variable y. Random variable y is the number of trials required to get the first success, and which is called as the waiting time distribution. Now we have to find out mean and variance of random variable y. Okay, now expected value of y, which is equal to expectation of x plus 1. Again this can be written as expected value of x plus expectation of 1. 1 is the constant and expected value of constant is equal to constant. Okay, therefore this is equal to expectation of x plus 1. But we know that expected value of x is equal to q upon p, that is mean of random variable x, which is equal to q upon p plus 1. This is expected value of y is equal to q upon p plus 1. Again, this can be simplified as q plus p upon p, which is equal to 1 upon p. Since q plus p is equal to 1, that is total probability is equal to 1, therefore expected value of random variable y is equal to 1 upon p. Okay, this is the mean of random variable y. Now variance, and variance of random variable y is equal to variance of x plus 1. Now variance of x plus 1 is equal to variance of x plus variance of 1. Okay, 1 is the constant and the variation of constant is 0. There is no variation, therefore which is equal to variance of x only. Okay, this is equal to variance of x, and we know that variance of x is equal to q upon p square. Okay, therefore variance of random variable y is equal to variance of random variable x is equal to q upon p square. This is the variance of random variable y. Variance of random variable y, which is equal to the variance of random variable x, but the expected value of y and expected values are different. Expected value of y is equal to 1 by p, and expectation of x is equal to q upon p. Okay, now we see the relationship between mean and variance of random variable x. Okay, relationship between mean and variance. In geometric distribution, variance of random variable x is always greater than or equal to expected value of x. Okay, now its justification is that since this p is less than 1, that is p lies between 0 and 1, therefore p is less than or equal to 1. This implies that 1 upon p is greater than or equal to 1. Okay, p is less than or equal to 1. This implies that 1 upon p is greater than or equal to 1. Now we multiply q by p on both sides of this inequality. Again, this implies that q upon p into 1 upon p, this is greater than or equal to q upon p. Again, this implies that q upon p square is greater than or equal to q upon p, and q upon p square is equal to variance of random variable x. This is greater than or equal to expected value of x. Q upon p is the expected value of random variable x. Okay, this is the justification of variance of random variable x is greater than or equal to expected value of x. Now we see moment generating function of geometric distribution. Random variable moment generating function of geometric distribution with parameter p. Okay, we know that probability mass function of geometric distribution is probability of x equal to small x, which is equal to p into q raised to x. Here x takes values 0, 1, 2, dash 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 up to infinity. That is, the support of geometric distribution is 0 to infinity, 0 otherwise. Okay, 0 less than p less than 1, and p plus q is equal to 1. Now, by definition of MGF or moment generating function, we have mx of t is equal to, this is the notation of MGF, moment generating function of random variable x, is equal to expected value of e raised to t into x. Now, by definition of expectation, this can be written as, which is equal to summation of e raised to t into x into probability of x equal to small x summation over x. Now, substitute here probability mass function of geometric distribution, which is equal to summation of e raised to t into x into probability mass function is p into q raised to x summation over x, x running from 0 to infinity. P is constant, take out of summation sign, then which is equal to p into summation of e raised to t bracket raised to x into q raised to x summation over x, x running from 0 to infinity. This e raised to t x can be written as e raised to t bracket raised to x. Okay, now again this can be written as p into summation of q into e raised to t bracket raised to x summation over x, x running from 0 to infinity. Now put x equal to 0, x equal to 1, x equal to 2 in this summation. Then we have, which is equal to p into in bracket. If we put x equal to 0, then the first term is 1. Then put x equal to 1, then second term is q into e raised to t plus next term is q into e raised to t q into e raised to t bracket square plus next one is the q into e raised to t bracket raised to 3 plus so on. Okay, now the sum of this series is equal to, which is equal to p into in bracket 1 minus q into e raised to t bracket raised to minus 1, which is equal to p upon 1 minus q into e raised to t. This is the moment generating function of geometric distribution, p upon 1 minus q into e raised to t. Okay, moment generating function of geometric distribution. Now we see cumulant generating function of geometric distribution. Cumulant generating function, cumulant generating function of geometric distribution, okay. We know that MGF of geometric random variable is equal to P upon 1 minus Q into e raised to t. Okay, this is MGF. Then this can be written as P upon P plus Q minus Q into e raised to t. We know that since P plus Q is equal to 1, total probability is equal to 1, therefore here we substitute 1 is equal to P plus Q. Now we divide numerator and denominator by P, then we have which is equal to 1 upon 1 plus Q upon P minus Q upon P into e raised to t. Okay, this is MGF of random variable x. Okay, now we obtain cumulant of geometric distribution. By definition of cumulant generating function, kx of t, this is the notation for cumulant generating function. Kx of t is equal to log of MGF, This is the definition of cumulant generating function. Then we know that moment generating function of geometric distribution is 1 upon 1 plus Q by P minus Q upon P into e raised to t. Okay, this can also be written as this is 1 upon 1 minus Q upon P into in bracket e raised to t minus 1. Now we put this MGF here, which is equal to log 2 base e of 1 upon 1 minus Q by P in bracket e raised to t minus 1 bracket complete. This square bracket complete. Okay, now this can also be written as minus log 2 base e of 1 minus Q upon P into in bracket e raised to t minus 1 bracket complete. This is kx of t. Kx of t. Then we know that e raised to t is equal to 1 plus t square upon 2 factorial plus t cube upon 3 factorial plus so on. Okay, now we put e raised to t is equal to this one in the above kx of t. Okay, now kx of t is equal to minus log to base e of 1 minus q upon p into in bracket e raised to t is equal to 1 plus t square upon 2 factorial plus t cube upon 3 factorial plus dash dash dash. This bracket is complete here, again here, and minus 1 is here. Okay. Now this plus 1 minus 1 gets cancelled, which is equal to again minus log 2 base e of 1 minus q upon p into in bracket t plus t square upon 2 factorial plus t cube upon 3 factorial plus dash dash dash. This square bracket complete. Again, suppose this is close, this is open, and this is close bracket. Okay, then again we use one result, log of log of 1 minus x, which is equal to minus in bracket this result is equal to what? X plus x square by 2 plus x cube upon 3 plus dash dash dash. Okay, now we use this result here. This can be written as kx of t is equal to this minus log of this value 1 minus x is equal to, this is x, then minus log 2 base c. This is can be written as this is equal to first value is q upon p into in bracket t plus t square upon 2 factorial plus t cube upon 3 factorial plus so on. This bracket complete, plus second term x square by 2, which is equal to what? Q upon p into 1/2 into in bracket t plus t square upon 2 factorial plus t cube upon 3 factorial plus so on. This bracket complete, brackets are square, plus q upon p into 1/3 into in bracket t plus t square upon 2 factorial plus t cube upon 3 factorial plus dash dash dash, bracket complete, brackets are square, plus so on. This is the cumulant generating function of geometric distribution. Now by using this cumulant generating function we can obtain the cumulants of geometric distribution, that is k1, k2, k3, k4 and so on. The cumulants of geometric distribution is equal to, by using this expansion, kx of t equal to, or k1 is equal to coefficient of t, k2 is equal to coefficient of t square upon 2 factorial, k3 is equal to coefficient of t cube upon 2 factorial in the expansion of kx of t. Okay, in this way we can obtain the cumulants of geometric distribution. Okay, thank you.